Hello, everyone. This is our final lecture on new material. It's the second part of chapter 15. It covers what are called mechanical oscillations. Some of what we did last time, we're going to go over again, except we're going to do it more fully, more correctly. Last time we kind of cut through a little bit of we simplified things a little bit. We're going to actually delve deeper into a more exact answer. And I'm going to show you how to find a more precise answer to the differential equations. So that being said, this lecture is going to be a lot of math, a lot of mind-numbing math. But I'm going to tell you why I want to do this. I want to cover this for you because you're all going to move on in engineering and the sciences. And really, our next step is to start examining systems using differential equations to derive the equations of motion. That's actually where you're headed. And I want to make sure that you've seen these solutions at least once. Hopefully you'll have teachers that go through it and do a really good job of explaining these to you as you go. But honestly, if you keep good notes on this and keep it off to the side, you may find this is the most useful lecture for later on in your academic career. What we're covering are harmonic oscillations. And that's just a fancy way of saying that there's a periodicity, there's a period to the motion. Harmonic oscillators describe all sorts of physical phenomena. They describe electrical circuits, they describe atoms or electrons in lattices, they describe cells moving around, they describe bungee cords, they describe so much stuff. And they're relatively simple to understand as long as you kind of know where they come from, where the equations come from. And that's really what I want to show you. We're first going to study what are called undamped oscillations, which means that there's no friction, there's nothing happening that's taking energy out of the system. So an undamped simple harmonic oscillator, pretty easy. At the end of it, we're just going to write down equations, and I'm going to show you how to attack these problems, how to solve these problems. The algorithm's really quite easy. There are the occasional kind of weird problem, but we'll talk about that. And hopefully by the end of this lecture, you'll be able to handle any oscillatory problem. And then we're going to talk a little bit about damped oscillations. Your book doesn't explain where the angular frequency for a damped oscillator comes from. I'm going to explain that to you. I'm going to show you the differential equation. It's a little hard, but you don't have to do it. You just have to understand it. And then we're going to talk about a couple of problems that show up in the homework problems for your book, but your book doesn't bother to explain it. That's when you have more than one spring, springs in series and parallel. And those equations actually show up in circuits, which is where a lot of you are headed next, to E&M or B. So I want you to see it. I want you to see all this stuff. The math on the back end, the math that you need to understand, remember, know how to use is relatively simple. How we get that math is a little hard. But it's fun, it's worthwhile, and it's really important that you know it. Like I said, I had a student tell me that they didn't cover these types of problems in their differential class, and I thought that was insane, because these are the most important physical equations for studying biology and chemistry and even a lot of engineering and a lot of electronics, just response functions. The whole idea behind an oscillation is that there's some equilibrium point And if you move the system away from equilibrium, it comes back. So it restores back to equilibrium, and it overshoots a little and it comes back, and it just constantly shoots around this equilibrium point. And like I said, most physical systems in nature work this way. So if you know this, you know most of what you need to know. If you go on to study differential equations in math, there's a whole bunch of other categories of differential equations and a lot of cool things. But this will get you through a lot of physical phenomena, which is kind of what the point of this course was to enable you to make predictions about the motion, the velocity, acceleration, and the energy associated with the system as it is displaced about some equilibrium point. Okay, so let's get started. We are essentially, as we did last time, going back to this idea that we have a system that looks like some mass. The mass is attached to a spring, and that spring has something called a spring constant K. The spring has a length L, and when it is at equilibrium, meaning if the spring isn't stretched or compressed, then the block sits at an equilibrium position where X is 0. And to the left will be negative, to the right will be positive. The only force acting on this mass has a magnitude of K times X. We assume that this spring generates a force which is the spring constant K times X. We assume it's an ideal spring, so K doesn't vary as you vary X. And because it's a restoring force, it gets a negative sign. And all that means is that if we pull the block this way, the restoring force acts that way. So if X is going that way and vice versa. If we push it that way, the restoring force tries to push it in the opposite direction. That's where this negative sign comes from. Okay? And so what we're going to try to do is describe this motion. The full equation, if we assume if A is this way, right, and it's being displaced in that direction, then the force is that way. And we can write an equation of the motion, Newton's second law, ma is equal to negative kx. But better would be to say that the acceleration is time dependent, and it's equal to k over m times some time dependent equation of our motion. Okay? So our job is to figure out what x of t is. This is what we're trying to figure out. We want to know what our position equation is. And we note that a of t is the second derivative of the time function, or the displacement with time function. If I move this over, I get plus km times x of t. And so I know that, and I set this equal to 0, I know that what I'm looking for is some function that the second derivative plus k over m, some constant times the original function, gives me 0. In differential equations, this is known as a homogeneous equation because this side is 0. The non-homogeneous equation has some constant over here. And basically, in the theory of differential equations, if you can find the homogeneous solution, you just assume that it equals 0 at first, find the solution to the homogeneous equation, then you can find the solution, the particular solution to the non-homogeneous, the side where the constant equals something, and you have your solution. That's nothing we need to worry about, but that is something when you take differential equations that you'll do. You'll solve this homogeneous part, and then you'll solve it for a particular solution. And that gives you the solution to the equation. Okay? And so we need to figure out what function, second derivative, gives back the function plus a negative times some constant. And because it's a second derivative, we know it has to be a periodic function, a function that comes back to itself. We know the periodic functions. The most simplest, easiest to remember are the sine and cosines. So I need to talk about something else really fast. But first, what I'm going to say is that x of t must be equal to a times cosine of some omega t plus b times sine of omega t. And I should also note that your book has this weirdly wrong. We'll see that in a second. But so before, this is what we used, and we said, oh, well, we're starting at time is 0, we're starting at a maximum, we'll kill off b. We're not going to do that today. Today, what we're going to do is we're going to say that a has to be some maximum amplitude times cosine of something called a phase angle. And that just tells us where this thing is going to start. Because when time is 0, we'll see, this becomes 1, and so this becomes the initial displacement of the object or the system at a time is equal to 0. And b, similarly, will be x max times sine of phi. And therefore, what we get, and we're not done yet, but we get that x max is cos of omega t times cos of phi plus sine omega t plus sine of phi. And we need to go back and look at our trigonometry for a second to make get a better, simpler solution for our displacement function. Okay, so when I have cosine of theta 1 times cosine of theta 2 plus sine of theta 1 plus sine of theta 2, you can prove in trigonometry or algebra, or wherever you learn this, you can derive this proof that this is equal to cosine of theta 1 minus theta 2. If these were sines, it would be positives, different orders to the functions, but that is this one. So when we look back, we can see that this is going to actually equal, x of t is going to equal x max times cosine of omega t minus phi, where phi is a phase angle. And note that your book gives this as a positive. I have no idea why your book gives that as a positive. I think I know. I think it's trying to make the it easier, but as you can see from trigonometry, this has to be a negative. And in fact, when you take differential equations, this is a negative. So just note there's a funky sign here. This funky, weird sign that your book is throwing as positive is actually a negative. And we'll talk about it more when we do one of the examples. But for now, just note it's a negative. One more thing that do not forget, the cosine of an angle, right, is equal to cosine of the negative angle. We can prove that just visually really fast. If we have 30 degrees and we have negative 30 degrees, cosine of these is the part of this hypotenuse that lies along the x-axis. And it doesn't matter whether this angle is negative or positive, right? Further, sine of theta, or I should say sine of negative theta, right? Sine of this negative is equal to negative sine of theta, okay? Just remember those things. You don't need them, but this is kind of important, that the cosine of an angle is equal to cosine of the negative angle, and sine of the negative angle is equal to negative sine of the angle. Okay, so we have, as I said, we have this function. This is our displacement function. Note that x max is a constant. omega, the angular frequency is constant, and phi is a constant. And really, our job is to figure out what these three things are, and then plug in some time, and we have an equation for the displacement. If we can do that, if we know omega, and we know x max, and we know phi, as I said, this is the maximum amplitude, the maximum distance that we pull it away from equilibrium, then the first derivative with respect to time, which is the velocity at time t, is x max times this derivative. And the derivative of this, because this is a constant, we pull an omega out, we get a negative sign, right? And we get an omega, and we get cosine of omega t. The derivative of the interior is omega. The derivative of cosine of an argument is negative sine of that argument. I don't like how I wrote that. I'm going to write it as this. Okay, just to make it a little easier. Okay, and then the second derivative of the position, or the first derivative of the function, or I mean of the velocity, is our a of t. And again, the derivative of this, an omega comes out, and the derivative sine of the argument is cosine. So we get a negative omega squared x max times cosine of omega t minus phi. And once again, we see that this is our x of t, and therefore a is simply minus omega squared times x of t, whatever x of t happens to be. Okay, I'm going to stop for a minute and write those. We're going to write them a bunch, but I'm going to write them again. So we have that x of t has to be x max cosine of omega t minus phi. And we have that v of t is x max sine omega t with a negative omega out front. And we have that a of t is negative omega squared x max of cosine of omega t. All right. One thing I want to say before we do anything else is when this argument, right? When this argument here is a maximum, we get the maximum velocity. So the maximum velocity, Vmax, is, we'll figure out what time that is once we talk about phi, but that is important. If we say we actually want the magnitude of the maximum velocity is just omega times x max. And a max similarly is okay. But back to our constants. So our job, in order to use these, we have to know what x max is, we have to know what omega is, and we have to know what phi is. And we're going to talk about each of these, starting with the easiest and moving on to the hardest. So the easiest is actually the amplitude. When this thing is at a maximum, it has maximum potential energy, right? And this thing is going to oscillate back and forth, right? So here it has max kinetic or max potential energy. We'll talk about that in a minute. And here it has max potential energy, and here it has max velocity, max kinetic energy. Okay. But whatever this maximum is, normally with these problems, we start off by pulling it to some maximum displacement and then letting it go from rest. Occasionally, you'll have a problem that you start analyzing the system and the system's already in motion, and you want to know what x max is. But we're going to assume that if we look at the problem tells us what our amplitude is. So this is just our amplitude. We'll go through a problem in a minute on how to find these for an easy problem. But before I get there, I need to talk about angular frequency and phase angle. So we saw that this was, from our force equation, we saw that this was true. And we can tell that A is actually negative omega squared x of t, A of t, I should say. Right? Therefore, just by inspection, we see that omega squared is k over m, and omega is square root of k over m. So those two things are known, right? Those are easy to figure out. Usually, I'll show you what to do when you're not just given k or m or x max, but for the most part, you can figure out what those are, right? However, the phase angle is a little bit weird. So let's talk about what the phase angle actually tells us. We'll start with this, okay? Now, how would we figure out the phase angle? Well, when t is equal to 0, we need to know where x is. So we need to figure out what x naught is. So in a very simple case, let's say we pull it out to x max, right? So we pulled this thing out to x max at t is equal to 0, and then we're going to let it go. So at x naught, x is equal to x max. At t is equal to 0, x is equal to x max. Now, when t is equal to 0, this term goes away. So what we get is that x naught is equal to x max times cosine of negative phi. But first of all, we know that this is also x max, right? And we know that cosine of a negative theta is cosine of theta. And therefore, we get that cosine of theta has to be x max over x max. Or writing it a little bit better, x at time 0 over x max. And we could do this arc cosine of x max over x max, right? But we know this is 1, and the value of cosine, the value of phi when cosine of phi is 1 is 0, right? So phi has to be 0 if cosine of phi has to equal 1, right? So cosine of phi has to equal 1, therefore the value of phi is 0. So when we're at a maximum to start at time 0, we know our phase angle doesn't exist. What about when we're at 0, right? So now let's talk about, we just start looking at the system, and at some time it's flying this way with some velocity. We don't know what x max is, right? But we know that x at time 0 is 0. And again, cos of phi is x at time 0 over x max. But it doesn't matter what x max is. If this is 0, right? If at time 0, this would be 0 over x max. I'm just going to write a little m for max sometimes. This is 0. So what is the value of phi when cosine of phi is equal to 0? Well, phi could be pi half, or phi could be 3 pi halves, or phi could be negative pi half, right? So what it is it's n plus 1, right? It's n plus 1 over 2 times pi for all values of n that are integers, including 0. So it could be, except for this can't be negative 1, right? So it could be 1. No, it could. I'm sorry. I'm being weird. It has to be n plus 2, right? No. What am I trying to do here? My values are 1, 3, 5, right? So it's when this is 0, it's 1. When this is 1, it's 3. When this is 3, it's 5. Yeah. Anyway, I don't care. I'm being weird. It's late. You already know this, so I'm not real worried about that. But basically, whenever this is 90 degrees or 100 or 270 degrees or 450 degrees, right? Every 180 degrees. It could also be minus 90 degrees, minus 270, on and on and on. But what we have to do, and the whole point of this, is we don't care about all the values it could be. We only care about the simplest value it could be. And the simplest value it could be is pi half. So we say that phi is pi half, right? If we come and we start measuring the system when it's at 0 to start with, when t is 0, x is 0, then our phase angle is pi half. So looking at this, if at t0 we start measuring and it's at x max, our phase angle is 0. But we have to add a phase angle when it's not at maximum. And why is that? So let's look at a couple different cases. So this is going to be x max, this is going to be negative x max, this is going to be 0. This is going to be x max, this is going to be 0, this is going to be negative x max. X max, 0, negative x max, and here. So I want to look at 4 different cases. All right, so first of all, when it starts at x max, and let's say this is t to the half, and this is, I'm sorry, t to the fourth, and this is t to the half, and this is 3t to the fourth, and on and on and on. I'm not going to write those every time. You'll understand in a minute what I'm doing. But here at t is equal to 0, x is x max, right? So it starts at positive x max, starts going down. I should really draw it like this, right? It starts doing some cosine function. Note that t is equal to 2 pi over omega, right? And I should note that these are 0. So if this is the full function is 2 pi, if I want a quarter of the period, that happens when we get 2 pi over 4 omega, or pi over 2 omega. Sorry, pi over 2 omega. And t to the half, likewise, is 2 pi over omega, or over 2 omega, or pi over omega. And similarly, t to the 3/4 would be 3 over 2 omega, and full t is 2 pi over omega, right? So here, at this time is pi over 2 omega, okay? It's at 0, but it starts at maximum. Now, if instead, and we'll draw this a little bit differently in a minute, if instead I start at 0, right? Well, depending on where I'm going, if I'm going this way, x is going to decrease. So I'm going to get this cosine that starts doing this, right? This cosine wave. And so basically what my phi is telling me is where to start my cosine at time is equal to 0, right? If I went back a little bit, this would go up, right? So when it crosses t is equal to 0, it's where in the cycle the particle is. Now, if I started at negative x max, again, t to the fourth, t to the half, right? 3t to the fourth, it starts at negative and it's going up and it comes up and it starts to go back, right? So this is when phi is negative. I'm sorry, not negative, although it could be, is pi. Because cosine of pi is -1. And this is when phi is 0. Because cosine of 0 is 1. So we start at x max or we start at negative x max. And here, this is when phi is pi half. Because cosine of pi half is 0. It could also be negative pi half. But cosine of theta is equal to cosine of negative theta, so it doesn't really matter. We know that phi has to be pi half, right? Or negative pi half. Whatever we get, it doesn't matter. So the last thing I want to show you here is those are all easy to understand, right? But what about if it's some weird, right? It's some weird place, like it starts at halfway at x mass to the half, right? Well, this thing is going to come off and be a little bit further, right? And then it's going to be a little bit further, and it's going to be a little bit further, right? Until it really gets back, that last part I drew. So it's a little bit past. Normally, it would be at 0. Sorry. So normally, it would go from here to 0, but it's going to go a little bit past 0. And then here it would go to -m, but it's going to be a little bit coming back from -m. And then it'd be back to 0, but it's a little past 0. And then here it would be back to xm, but it's actually back to where it started from. And I know those don't look like great cosine curves. I could draw them as better cosine curves. But the point is that here we have no idea. We have an idea. What we don't have is we don't have a nice function for phi. But we still have that phi is arc cosine of x initial over x max. So all you have to do is look at the distance from 0 to here divided by the whole distance, and that gives you your phi. Okay? So generally, what you do is to find phi, you calculate when x is 0 that x max is cosine of omega t minus phi, and you say that that's 0, right? So this is x max cosine of phi. But you can tell, since cosine of phi is x naught over x max, you can tell right away if the object starts at positive x max, right? So if that's equal to x naught, then phi is going to be 0. And if it's negative x max is equal to x naught, then phi is going to be pi. And if x max, I'm sorry, if 0 is x max, is x naught, then phi is going to be pi half or negative pi half. And for anything else, phi is cosine of arc cosine of x naught over x max. And again, all this is telling you is where the cosine function begins at time 0. It's where the cosine function is at time 0. Often in these problems, you're just going to look and go, oh yeah, it's starting at x max. I can just say phi is 0. On an exam, quiz, whatever from me, I will often ask people, what is phi? How do you know? Or I might tell you phi is 0 and ask you, how do you know? And the answer is, you know, because it begins at the maximum value of x. Or phi is pi because it begins at the maximum negative value of x at a negative amplitude, right? The wave begins at negative x max. That's not too hard, but just be aware that it can be a little bit tricky. There is a pure mathematical way to do it here. I'm going to show you another way to get it in a minute. But this is one way of finding it. This is by inspection, kind of, which isn't too hard, but it takes a little bit of practice to figure it out. Okay, so let's remember that by conservation of energy and work, the work energy theorem, the change in kinetic energy is the change in potential energy. Potential energy of a spring was kx squared over 2. Kinetic energy is obviously mv squared over 2. And therefore, the energy at any time is mv squared over 2 plus kx squared over 2. And conservation of energy says energy at time 1 is energy at time 2. So this would be m times v1 squared over 2 plus kx1 squared over 2 is equal to mv2 squared over 2 plus kx2 squared over 2. And if you knew these, you can just plug in knowing that v1 is v at time 1. You can go back to that velocity equation and plug in what time 1 is, and x1 is x at time 1, and figure out what these are, assuming you know k and m and omega and v, right? And similarly, v2 is v at time 2, and x2 is x at time 2. That's pretty easy to understand. One really cool thing about this, though, that we should notice is mv squared over 2 plus kx squared over 2. This is equal to m over 2 times negative omega x max sine omega t plus v, all of this squared, right? Plus k over 2 times x max times cos omega t minus v, all squared. I don't know why I wrote that. Okay, so let's look at this. Right, let's look at this, and we get that m over 2 times omega squared times x max squared times sine squared of omega t minus v plus k over 2 x max squared cos squared omega t minus v, right? Now, knowing that omega is actually k over m under the square root, this becomes k over m squared, and this whole thing becomes k over 2. And so we see that k over 2 times x squared x max squared is sine squared of this argument plus cos squared, or cos squared plus sine squared, but that's 1, right? So this becomes k over 2 times x max squared times cos squared omega t minus v plus sine squared omega t minus v, which is k x max squared over 2. The energy at any time is equal to the spring constant divided by 2 times the maximum amplitude squared. And so you could set the energy at any time, k x max squared over 2, equal to m v squared over 2 for some time, plus k x squared over 2. I'm just going to put a little t here. So sometime. This is just a constant value. By conservation of energy, there's no friction, there's nothing else doing work on this system. And therefore, you pretty easily can see you have a nice equation. In practice, what we really do is this is really just an analysis. Once we already know our A and our B and our X equations, which we need to know anyway, what we would use the energy for is to find V or X. And since we have those equations and we can just write them down, in general, it's not that useful to know the energy. It's useful, like I said, to do the analysis because the energy has to be conserved, but it is a good thing to know, okay? So before we move on to the two examples that I want to do of how to do all this stuff, I do want to go back and just write everything that we've learned so far that you need to remember. So you need to remember that x of t is x max times cosine of omega t minus v. And you need to know that vt is negative omega x max times sine omega t minus v. And you need to know that a of t is minus omega squared x max cos omega t minus v. Few things that are important to know. The period is 2 pi over omega. Omega is square root of k over m, which also means that omega squared is k over m, that x max is the max amplitude, okay? And phi, you can find by arc cosine of x at time 0 over the maximum x, okay? And then lastly, that the energy at any time is k times x max squared over 2, and that's equal to mv squared over 2 plus kx squared over 2 for some given time, if you need it. And that's it. That's really all you need to remember. The algorithm is you need to figure out what phi is. You need to figure out what x max is. You need to figure out what omega is, or k is, or m is. You need to figure those things out, and then all you do is plug them in. You plug them into x max, omega, and phi in these three equations here, or into this energy equation, or whatever, okay? There is a nice tricky problem that I'm going to go over that's an example in your book. It's one of the ones I really like in your book. We'll do that in a minute so you see how this works. But as far as things you need to remember, this is it. The equation's given to you. You're really just trying to find variables and then plugging in time and figuring out what the velocity or the acceleration or x is at some given time in the motion. I should also note that, remember that the magnitude of Vmax and Amax, the magnitude of the maximum velocity is this, and the magnitude of the maximum acceleration is this. When that occurs, we'll have to figure it out, but so those are all good, right? I should say that because this Vmax is sine omega t minus phi, this would occur when omega t minus phi is equal to pi half. And similarly, Amax and Xmax occur when cosine of omega t minus phi is equal to 0 or 2 pi or whatever. So that's not super helpful or necessary to remember. This is usually all we care about, but you could find it if you needed it. Anyway, let's move on to a quick example. In the following example, I'm going to say that I have a 4 kilogram mass attached to a spring with a spring constant of 200 newtons per meter, right? And originally, I pull it out a distance of 2 meters, and at time t is equal to 0, I release it. So at t is equal to 0, x of 0 is 2 meters. And from all of this, from this information, what I want to know is I want to know what is a, well, what is x, what is v, what is a at any time. And then I'm going to ask at specific times. So how we start this is we need to find x max, we need to find omega, and we need to find v. Now x max, we already see that we pulled this thing out 2 meters. So we're at maximum when we start. That's easy enough to understand. Omega is square root of k over m. And we were given k and we were given m. So that's also not too bad. This is 200 over 0.4. Square root of 50 is 7.07 rad per second. Okay, so now we have omega. And finally, for phi, if we want to do it the cosine way, cosine of phi is x naught over x max. But we know that x naught is 2, and we know that x max is 2. So we can see that this is 0. And we're not going to have to worry about, in this particular problem, any phase angle, because it starts at maximum. So from this, we can quickly write down for x of t, and I'll do the same later for everything else, but x max, I'll just do it. Getting lazy because it's late. X max, cos omega t minus phi, omega sine omega t minus phi, and cos omega t minus phi. And so from these, I can just plug in for x max 2. I know that phi is 0, so I get 2 cos, and this was 7.07 times t. Similarly, I know that omega is 7.7. So if I wanted to, I could write 2 times 7.07. That's x max times omega times sine of 7.07 t. And finally, I would get minus 7.07 squared times 2 times cos of 7.07 t. Right? Not too hard. But that's all you really have to do. At this point, we have an equation for x, we have an equation for b, and we have an equation for a. So let's write those again really fast. X of t was 2 cos of 7.07 times t, and b of t and a of t, right, was negative 7.07, so 14.14 sine of 7.07 t. And this was 7.07 squared. 7.07 times 7.07 times 2, which is about 100. So this is about 100. Oh, of course it's 100. It's the square root of 50 times 2, or squared times 2, times cosine of 7.07 t. Okay? So now that I know those things, I could ask for the energy, right? And that would be k x max squared over 2. And this was 200 over 2 times 2 squared, which is 400 joules at any time. And I could say, well, if I want to know the velocity at time t, I could use mv t squared over 2 plus kx t squared over 2 and set this equal to 400 joules and blah, blah, blah. But why not just plug in or just solve this, right? I mean, yeah, I guess that's useful. If you knew what x was and what v was, you could figure out what time was, right? That might be a transcendental equation. Don't care about that so much. What I do care about is this. I want to know at a time of a time that is equal to pi over 2 omega, right? So this is pi over 2 times 7.07, for instance. I want to know what x, v, and a are, right? And I wrote it this way for a reason. X of pi over 2 omega, I can easily see that this is 2 times cosine. Remember, this was omega times 2 pi, times t, but t is pi over 2 omega, right? And so this is cosine of pi half, which is 2 cos of pi half That's 0. So at a time of pi over 2 omega, whatever that happens to be, I know that I'm at equilibrium. V at pi over 2 omega is omega times sine, right? Times omega times pi over 2 omega, which is 2, I'm sorry, I forgot my x max, right? Which is minus 7.07 times 2 times sine of pi to the half, which is 1, right? So this is actually 14.14 meters per second with a negative sign, and it's a maximum. It's crossing through the equilibrium point, and it's a maximum. And then A at pi over 2 omega is, again, I don't even have to do this. I can just look at cosine of omega times pi over 2 omega is cosine of pi over 2, so this is 0. And what that's showing is this, at this particular point, this was 2 and this was minus 2, my block is actually passing through 0 at a time pi over 2 omega. Because there's no phase angle, if there was a phase angle, it wouldn't necessarily be at equilibrium. But without a phase angle, at a time of pi over 2 omega, is passing through equilibrium where V is a maximum, X is 0, and A is 0. There's no acceleration because there's no force. Remember, the force is minus kx, but if X is 0, there's no force acting on this block as it passes through the equilibrium point. We could similarly, and you could do this for yourself, you could put in a time of pi over omega. And if you did that, you would see that this would be pi over omega would give you cosine of pi. So you get X as negative X max, and V is 0, and A is negative omega squared X max. That's because at this time of pi omega, it's at the other maximum, the negative maximum, the negative amplitude. And you can see that for yourself. What I'm really just trying to get at with this is that the idea is find constants, omega, maybe k, maybe m, x max, and phi. So find those. Usually they're given to you. You might have to do something to find them, but find them. And then write your equations with the constants. Okay? So you write x of t, for example, is whatever x max happens to be, cos of omega t minus phi. And you write them down for x and v and t are in A. And then the last thing is, so 1, 2, the last thing is usually to plug in some given value of t to figure out something meaningful. What's the velocity at a time of 38 seconds? What's the acceleration when x is half of the x max, right? Things like that. You can find all sorts of relevant things, but you've done the hard work already. And it's really not that hard. If you can find omega, k, m, x max, and phi, you're good. There's not a lot to these problems, to be honest. How can they get tricky? Well, here's how they get tricky. This is a problem that's given in your book. And there's a couple things I want to cover with it, but it's actually a really kind of neat problem. It's something that you would see in real life, let's say. And in this problem, we're told that we have a mass and it's just past equilibrium and it's traveling in the negative direction, okay? And we're told this is at time is equal to 0, it's at some negative x value. It happens to be 0.85 negative meters. And the velocity at time 0, so we start checking on this thing and it's already moving to the left with a velocity of 0.92 meters per second. And finally, we're somehow able to deduce that it has a positive acceleration. It obviously does, because the force from the spring is trying to push it back as the spring is getting compressed. And what we want to know is what is x of t, what is v of t, what is a of t, etc., etc. What is the energy at any time? Okay. So we want to somehow get our equations out of just knowing this information here. The nice thing is, you know that x of t and v of t and a of t, you already know the form. This is x max cos omega t minus phi. This is x max, sorry, I'm gonna write this a little bit different. Negative omega x max cos x max sine omega t minus phi, and negative omega squared x max cos omega t minus phi. Right? Cool. So how does knowing the displacement, velocity, or acceleration at time zero help us determine what these equations actually are, what the constants are? We need to find x max, we need to find omega, we need to find phi. And how we're going to do that is actually quite clever. So I'm going to actually find omega first because it's the easiest. Note that a naught over x naught, right? This is minus omega squared times x max times cosine of omega t minus phi. And don't forget that cosine of a negative angle is equal to cosine of the angle, right? Doesn't matter here because notice these cancel, right? And so we have Sorry, I had to let my dog in. So what we have here is we have that omega squared is equal to negative a at time zero over x at time zero. And we were given those, right? Or that omega is negative a naught over x naught. And you know that a and positive x is negative. Therefore, this was negative 47 over negative 0.085 or whatever. This is 23.5. So omega is 23.5 rad per second. Not too bad, right? Pretty easy to do. How are we going to find x max? We're actually going to save that for last. Before I find x max, I want to find phi. Okay? And the preliminary thing that I can see here is that if I use v over x, I can actually solve this for phi. V naught over x naught is equal to negative omega x max times sine, remember that this is zero, so this is sine of negative phi, over x max cos of negative phi. However, sine of negative phi is negative sine of phi. So this is a negative sine times a negative omega. X max is cancel. I get omega sine phi over cos phi, or turning that into a tangent, I get v at time zero over x at time zero is equal to omega at tan of phi. Or I get that phi is arctan of v at zero over omega times x at zero. And I have to warn you right now, This is where me and your book differ. We differ a lot here, okay? So I found that phi was tangent of arctan, I should say, of v of 0 over x of 0 times omega. And this is arctan. Remember that v was negative and x was negative, therefore there are going to be no negative signs. So this is 0.92 over 0.085 times 23.5. Okay, and I get that this ends up being arctan of 0.92 divided by 23.5 times 0.085. I get 24.73 degrees. If you're following in your book also gets 24.73 degrees, except it gets it, I believe, as a negative number. So remember when I said that your book gives you x of t as x max of cos omega t minus or plus phi. This is what your book gives you. And I said it should be minus phi. This is what the math gives us, right? So this is actually wrong. And doing this with a negative sign, I get a positive angle here. I need to remember that theta, or phi, because it's tangent, it could be, you could add 180, which would give me 204.73, or I could subtract 180, which would give me negative 155, 155.3, let's say. It could be any of those angles because tangent is actually a multivariate function. So how do we figure out what angle it should actually be? Well, it turns out that we know that x max has to be positive, right? And we know x at time 0 has to equal x max times cosine of whatever our phi is with a negative sign, right? But it's cosine. It can be a positive sign. It doesn't matter, right? This has to equal x naught. And x naught, we already know, was negative 0.085 meters. xm cannot be negative. It has to be positive. It's a positive number. Therefore, cosine has to be negative, right? And cosine of 24.7 is positive 9.08. And cosine of 204.73 is also, well, is negative 9.08. Okay? So it could be cosine of 204, or it could be cosine of 155. What is cosine of negative 155.3? It's negative. They're the same angle, right? So we can choose either of those. The thing is, and this is where things get hokey and weird, is that cosine of 204 is wherever, right here, right? Ish. And that's equal, so this is 204 and this is negative 155. 24 is here. So we're going to choose this value, okay? We're going to choose that phi is negative 155.3 degrees, right? That's where we start from. And if we look at this, then we get that x naught was xm times cosine of negative phi, which is xm of cosine of 155.3 degrees. You can turn that into rads if you want, it doesn't matter. So what is xm? Xm is x naught, x at times 0, over cosine of 155.3 degrees. And we see that this ends up being negative 0.085 divided by cosine of 155.3, which is 0.09636, 0.0936, which is incidentally what your book got. Your book gives you that phi. Your book's answer to this is phi is 155 degrees and x max is 0.094 meters or 9.4 centimeters. It's weird because whether you say phi is negative or positive in the argument of cosine, it doesn't matter. It will matter in the argument of sine. Therefore, we better see which one of us is right. We know, okay, that the velocity has to be negative, right? The velocity has to be negative at t is equal to 0. So I'm not sure if I'm going to be right or the book's right. I might have something messed up here. We know that the velocity is x max times omega with a negative sign, right? So this is v at 0 times sine of omega t minus phi, and this is 0. So we have a negative 23.5 times 0.094 times sine of 155, okay? And sine of 155 is positive, right? It has to be positive, okay? And furthermore, we know that this number is going to be negative, and it needs to be negative. So let's make sure we get what they got, just to make sure our math is cool. Sine of 155.3, really, I guess. I get 0.92, which is exactly what we had with a negative sign. I get negative 0.92. So I maintain that the actual function here is x max cos of omega t minus phi. Your book says it's a plus phi. And I say that phi is negative 155. Your book says that it's positive 155. I don't know what to tell you. I don't really understand if maybe it's just a typo on your book's part. It doesn't appear to be because they carry it through the rest of the math. But if I were you, I would use negative phi, okay? However, that being said, I'm not going to penalize you if on an exam you mess up the sign on phi. What I care more about is that you understand that phi is a phase angle, and it tells you where to start your where to start the cosine function, where the cosine function begins when time is equal to 0. I hope that makes sense. Okay, so on to the rest of this chapter. I will say is a lot of information and not a lot of math. Here we have something called an angular simple harmonic oscillator. And what that means is you could have like a pair, I think it shows in there, that's spinning. And it's spinning with some period, okay? And we know that there's got to be a torque on here. So it's spinning because there's some torque acting here that we can describe as K okay? That's all this is saying. And furthermore, this torque is going to be negative. It's actually, I think I've drawn this backwards, sorry. I've drawn it positive and it should be negative. Why should it be negative? It doesn't really matter. When you read this part of your book, just know that you know a torque is I alpha. We already kind of did this with a pendulum, but this is actually called a spherical pendulum. It's rotating in this plane and it's got some negative torque on it. And therefore, because alpha is negative k over I, and alpha is the second time derivative of theta, you know that omega for this is the square root of k over I, where I is the moment of inertia around this z-axis, this axis that's rotating, and k is some friction constant in the string itself. That's why things spin back and forth. This problem is ridiculously easy, plug and chug. If you read, it's section 15.3. Just read it. There's literally nothing to this. We actually covered everything in torque or in pendulums that would even come close to applying here. And all they do is they figure out, I think, the mass from a really easy problem with a rod versus this rotating pair thing. That's really simple at this point. I don't think you need me to explain it. So moving on to damping. And damping, I warn you, this is going to get really, really complicated. We've already seen that our equation of motion was that ma is equal to minus kx. But imagine now if there is not only this force, but there is some force, maybe it's air resistance, maybe it's friction, but there's some damping force. And we're going to assume this damping force has a form beta times v, that it depends on the velocity and some constant, okay? So our equation of motion, Newton's equation, is that there is a force of damping and there's a force due to the spring as this thing slides that way. It tries to stop it, okay? Let's put that in the form of a differential equation. And I'm going to actually switch these. B dx dt plus kx is equal to 0. And note, this is the second derivative of x, this is the first derivative of x, this is x. Okay. This is, again, a homogeneous differential equation. All we've added, the only physics we've added is some friction or damping, some resistant force, some force that's resisting the motion. And we gave it this form of some coefficient beta times the velocity. This is a lot like what we did for air drag way back, chapter 4 or 5 or wherever we did that. I think it was 4. So it's a super simple model. If you can model the drag force on it as some number times the velocity, you've got a drag force. You've got a damping force. Some frictional force is what that is. So how do I go about solving this equation? Because now I need something that the second derivative times m plus the first derivative times b plus k times the original function gives me 0. And you look at that and go, I don't know. Even if I guess, I don't know. Well, it turns out that how we solve this is rather strange. We should recognize that this is equivalent to a quadratic equation, right? In a weird sense, we can assume this is exactly like a quadratic equation. And remembering that how we solve a quadratic equation is we find the roots 1 and root 2. I'm going to write these funky gammas here for them. Are b with a minus sign plus or minus b squared minus 4ac over 2a. Now our a is m, our b is b, and our c is k. And what I get here is I get minus beta times beta squared minus 4m times k divided by 2m. Okay, and let me go to a new page on that. So I get that my roots will be beta with a negative sign divided by 2m plus or minus the square root. I'm going to put the 2m in here, so it becomes 2m squared inside, minus 4mk divided by 2m becomes 4m squared. So this is 4mk divided by 4m squared, and I see that this becomes k over m. Furthermore, I want to write this as omega prime is actually the inverse, the negative sign of that. If I pull that inside, is km minus beta over 2m squared. And I also notice that this is my old friend minus beta over 2m squared. Okay. I think I skipped a little bit ahead, so I'm going to skip around for a minute. But this quantity here, if you look at the constants in there, the constants in there are whatever my drag or friction coefficient is, and my spring force and my mass. And somehow I need to figure out a solution that utilizes this. And it turns out it's pretty easy. The new equation of the motion, just like before, is x of t is going to be well, it actually depends. It really actually depends. So let's actually skip down to the 3 cases. So there's 3 cases here, and I need to remember that x1 and x2 are beta over 2m with a negative sign plus or minus k, nope, plus beta over 2m squared minus k over m. Okay, so I have 3 cases with 3 different solutions here. I have a case where if beta squared over 2m basically if this is greater than k over m, right? And just to be clear, there is a negative sign here, and to be clear, these are 2 different solutions, and we'll talk about that in a minute. But if the drag force squared is greater than the spring force divided by m, what happens is we get solutions that look like this. X of t is equal to a times e plus number 1 plus b e to the minus that. These are exponentials with that there. And what this graph looks like is if it starts at something, it just dies exponentially, right? Assuming that the drag force is greater than the spring force. So what's actually happening, what you'll see is that the drag force beats the spring force, and spring force can't even oscillate, it just dies exponentially. The second case is a little bit harder to describe. If b squared is equal to k over m, and therefore this becomes 0, what we get is we get this weird, really weird function that is a plus b times t times an exponential decay of beta over 2m times t. And this is some weird kind of, there's some weird periodicity trying to happen, but it doesn't quite get there, right? So it's trying, but it's this weird response function that you don't really need to know about, because this is almost never the case. But essentially, they're both doing their part, and you get weird stuff happening. But the last one is the one that makes the best sense. And that is if k over m is greater than beta over 2m squared, which is another way of saying if the spring force is much greater, the spring constant, I should say, is much, much greater than the drag coefficient squared, what we get is this really nice x of t is equal to x max times e to the minus beta over 2m times t times a cosine omega prime t plus b sine omega prime t. And we'll talk about that in a minute. But the bigger takeaway is actually right here. And this is our x, and this is our x max with a negative, and this is our x max with a positive, and this is t going that way. And what we get is, let's say it starts at x max, it tries to do this periodic motion, and then it dies. And you get this nice envelope curve, which is because of the drag force, right? The drag force is this exponential decay, and then this periodicity of cosine omega prime t, right? Where, as we said before, omega prime is equal to k over m minus beta over 2m squared, okay? Your book basically says if there's damping, then the new angular frequency is this. And it gives you this function, and it gives you this function with a plus again. A and B are still cos phi times, I shouldn't have put x max there, sorry, are xm cos and sine. So this becomes x max times e to the minus beta over 2m times t times cosine of omega prime t minus phi. So it's exactly like the function that we had before, but it's being multiplied by this weird exponential decay term. And that's because as it moves back and forth, it loses energy. The period actually gets longer and longer as it goes, and it slows down until it stops, which is kind of cool. You can probably think of a lot of things in real life that do this. You start swinging on a swing, and you go back and forth, and eventually you slow down and stop. You know, like a bungee cord someone jumps with a bungee cord, and if they could bounce up and down and up and down, and eventually they would stop, right? So it's motion that decays with time. And the energy here, your book takes a cheat. I'm going to cheat on it too, because I don't want to get into it. We'd be here for another hour. But basically, if you can say that K over M is much, much greater than beta over 2M squared, then you can assume that basically the amplitude is X max times E to the minus beta over M. I'm sorry, beta over 2M times T. And if the amplitude is that, then the energy at any time you could figure out by using K squared over the amplitude squared, which is actually K squared over X max squared. And here, if you square this, the 2 goes inside, and the 2's would cancel. And so you get E to the minus B times T over M. And that's the energy at any time, assuming you had damping. So you can figure out what the energy is. You could figure out what X is. It becomes a huge, this hand, mv squared over 2 plus kx squared over 2 is equal to the energy. And you could find the velocity by finding x from this equation. Find x from this equation, and you would get that mv squared over 2 is e minus kx squared over 2. And just plugging in omega prime, assuming in this case you have to know beta, but you could find v here quite easily. So you can do things with this. In real life, what you do is you map it. I don't know why you would, I don't know why you necessarily need to know the energy. Maybe you would. But the whole point of me showing you this is that when you do damping, you basically get this other force added on. Differential equations, there's multiple strategies. There's strategies for every type of differential equation, and this is second order with constant coefficients or whatever this is. And you solve these by finding the quadratic solution, and you just know that the solution is this. Now, if you want to, I should be a little bit more clear here too, by the way. This is beta over 2m times t. If you wanted to, you could take the derivative of this, which means taking the derivative of the exponential and the cosine using the chain rule to find v. Do the same to find a. That's a huge pain. I'm not going to do it for you. You can do it if you want. But just know that there's 3 different solutions. This is, as we said, this is the exponential if drag wins over the spring. If the spring can't compete with the drag. If they're equal, it does something really ugly and weird. And if the spring force, it just slowly loses periodicity, or the periods just get longer and longer and longer, basically. It gets longer between coming back to the amplitude, but the amplitude's also dying, right? So the amplitude is dying as x max times this e to the minus beta over 2m times t function. So the amplitude just decays until it stops moving, if it ever stops moving. And there's a lot of math to learn to go with that, but that's what you do. You assume this is right. We could check this. I'm not going to, but you could check it by taking the second derivative of that function, the first derivative, and 1, and make sure that they all end up being 0. I would probably just trust that it's true. Okay. What you need to know here is you just need to know omega prime, and you need to know the E, and you need to know that this is true. So know the form of the function here, and know that the energy at any time is K over 2 x max squared e to the minus bt over m, and know that this is actually K over m, and that we will always be in the regime where the spring force wins. Okay. All right. So a couple more things. This one's kind of cool. So everything, buildings, bars, swings, you probably know this. If you've ever played on the playground with swings, if you drive a system, and what driving a system means is that you supply energy into the system. Instead of taking energy away, you add energy. It turns out that if you add energy at the natural frequency, so if the system has something that looks like this, right? If you drive this being K over M, if you drive a system at this same frequency, so if the drive frequency is omega, basically what you end up doing is putting energy into the system that doesn't leave, assuming there's no friction, right? Well, I guess you always put it. But at resonance, you could theoretically put it in at this perfect frequency, and you would just drive it. And what would happen is, as it goes back and forth, is getting bigger and bigger and bigger as you're adding more and more and more. This is one of those times where you need to go out and read up on this. Tesla, the really, really awesome electrical engineer. Tesla is an amazing scientist. He supposedly made an earthquake machine that you could attach to a building, and if you set it at their natural frequency, it would shake the building apart. Because everything has a natural frequency that if you add vibrations at that frequency, it will literally just start absorbing energy until it shakes itself apart. We've seen this happen in earthquakes when the ground is rolling at a certain resonant frequency. There's engineering ways to make sure that that doesn't happen. Engineers should know all about driven resonance. We technically don't need to know anything about it, to be honest, other than, like your book says, the driving frequency is omega. There's a cool Mythbusters show where they try to break a bridge apart by walking on it. The frequency of the soldiers stomping creates a resonant frequency of the bridge, causing it to shake up and down and putting more energy in until it's violently going up and down and breaks itself loose. There's, I think, a video somewhere back east of bridges that fell because the trains going over them were causing resonant frequencies, were causing them to oscillate. That's another thing that I should add. Bridges going up and down oscillate. They're an oscillating system, and you can analyze them the same way. So yeah, it's all really cool. Resonance is simply adding energy in. You're driving it, which causes the period to increase because it causes the energy to increase and causes other things to happen, which is cool. Maybe it doesn't cause the period to increase now that I'm thinking about it, but it causes the energy to increase because it causes X max to get greater. And assuming that K stays the same, the energy increasing just gets out of control, which increases the velocity. Anyway, cool stuff to look up. Nothing in our book worth knowing about resonance, to be honest. You can read it. It's pretty neat. The last thing I want to talk about, and this is the last thing I'm going to cover for you guys all semester, I am going to post solutions to this homework that from last week and the homework that I do today, or that I do this week for you, that'll post Thursday. And then next week, I'll make sure you get, probably Monday, some solutions to it. But the last thing I want to talk about is springs. And what we haven't really talked about is what if we have multiple springs? So we've been talking about, well, it's a block connected to a spring. But what if it was a block connected to two springs? Or better yet, what if it was a block connected to two strings or springs like this? How do we handle these? Okay. Well, this situation is the parallel situation. And this situation is the series. I should say, actually, what I really want is two springs hooked together. We'll actually do all of these really fast, but these are also series. So you have series where they're on either side and series where they're both connected and they're connected to the block, okay? We're gonna start with parallel, and if they're parallel, we assume here that they need to, so MA is K1x1 plus K2x2 and x1, I'm sorry, K1 and K2. And in order for this system to work in our simplified world, I should say negative, right? X1 and X2 would better be the same. We can't be pulling one of these more than the other, right? They're going to both be pulled. If they have equal rest lengths to begin with, then they're both going to be pulled the same X, and therefore they're going to have the same K, right? Otherwise, the block's going to try and turn and rotate, and we don't want any of that happening. So from what you see here, K1 has to equal K2, X1 has to equal X2, and it's pretty easy to see that A is negative 2K, so difficulty K since they're both equal, over M is X, because this is X and this is X, and therefore omega is simply 2K over M. That's not too bad, right? You just end up with a 2 in there, right? But these series ones are actually kind of tough. So in our first case, we have spring 1 and spring 2. And as it moves this way, this is K1 and this is K2. Notice that force 1 is going to try and push it back, and force 2, the force from the second spring, is also going to try and pull it back. So we know that K1 and X1 plus K2 and X2, right, has to be equal to the force acting on it. And we assume that this force is some K effective times X. But we know that X is the same for everything here. So again, this is quite simply K1 plus K2. That's not too big of a deal. That's pretty easy to see. It's not a major problem. It is what it is. It's sorry. I think I need to actually talk a little bit about this. Their X1 and X2 are equal, right? Yeah. All the X's are equal. Therefore, this is true. And therefore, omega is K1 plus K2 over M square root. But now we see that if we have two of them, so now if we have two springs attached, okay, then what happens is this force and this force have to be equal to the force on the block. So the effective force. And the effective force is going to be K effective times delta X. But this is K1 X1 and this is K2 X2. right? So we know that delta x has to be x1 plus x2, right? And the forces all have to be the same. So we know that k1 x1 plus k2 x2 has to equal k effective no. Sorry. I'm getting ahead of myself. It's late. So what we see here is that k effective, right, times delta x, right, that is our k effective. And what we're going to say here is that x1, right, is equal to force 1 over k1 from here, and x2 is equal to force 2 over k2 from here, and k effective is equal to force effective over delta x, right? I'm sorry. No. Sorry, it's really late here. And therefore delta x is force effective over k effective. Okay, so let's do this. We're going to say that we want to know what force effective over k effective is equal to delta x, and therefore is equal to x1 plus x2, right? Which is force 1 over k1 plus force 2 over k2. And here is the one part of doing this that where you have to understand something. Force 1, the force acting from this spring, and force 2, the force acting from this spring, and the force acting on the mass, all of those have to be equal. If the forces aren't equal, the springs would bunch up and weird, bad things would happen. So this being equal, right? With all of those things being equal, we could just divide by F. And what we get here is, and this is going to be really important, we get F over K effective is equal to F over K1 plus F over K2. And therefore, if I divide through by F on both sides, I get that 1 over K effective is equal to 1 over K1 plus 1 over K2. Now, if I take the inverse of both sides, I basically flip these over, I get that K effective, and I would need to multiply this by K2 over K2 and this by K1 over K1. I see that I get K1 times K2 over K1 plus K2 is my K effective. And therefore, A is equal to minus K effective over the mass of my system times X, or that omega, in this particular case, is K1 times K2 over K1 plus K2 over M. And that is the solution to series when I have two of them in series like this. If they're in series like this, assuming I didn't mess that up, so would this be the same? X and X would be the same, therefore X would be K1 over, yeah, if all the X's are all the same and all the forces are all the same, then all the K's are all the same. So you just add them together. Pretty sure I did that right. But in this series of two springs on a mass, you get this weird dependence, this weird K product And what you're going to find, the reason why I bring this up, other than it's like problem 21 in your homework, is this is a lot like when you do resistors and capacitors in series and parallel, you're going to see this behavior too. And it's worth knowing how to deal with it. Thinking a little bit about this, that essentially what we have is A is minus K effective over M times X, and then you find K effective as we did. And in the other ones, you could find them by just adding. But here we had this weird K effective because they were lined up together. And the force on one and the force on the other had to be the same, but they had different Ks. You can also see that if the Ks were equal, you would get K squared over 2K, which would be just K, right? I'm sorry, K to the half, right? So if the Ks were equal, you get K squared over 2K, which is K over 2. But if they're not equal, you get this weird function. Okay. Anyway, for what it's worth, that is what it is. Few examples of physical examples of simple harmonic motion. Like I said, atoms, for those of you who are going on to physics or engineering, maybe even chemistry, atoms in a lattice will move back and forth some interdimensional distance as if they were on two springs that are equal. And so you get this, like we just talked about. That is a system that we would use this on. You could use it. One problem I gave was, imagine at low tide and at high tide, you have a buoy out in Newport, and it moves up and it moves back down every 12 hours. So this is simple harmonic motion, where you could find the energy if you knew the mass of the buoy, and you could figure out, knowing the period, you could figure out what omega is, because the period is going to be 12 hours. There's the tides come in and go out every 12 hours. So omega would be 2 pi over a period of 12 hours, which is what, 43,200, right? Seconds. And you could find omega, and knowing the low tide and high tide numbers, you could figure out what X max was. Imagine high tide was 2 feet. Let me say meters. Say it was 2 meters, and this was minus 1 meter. So there were 3 meters total. So X max would go from 1 to 3, right? Or it would be 1.5 meters. That would be the midpoint would be 0.5 meters. But basically, this would act like a system that was in equilibrium around 0.5. So it would act like this, and you would get this equation that said X max, what cosine of omega t minus phi. And if we assumed at the start that we were at low tide, phi would be negative, or would be pi, sorry, right? And so you can see we have 1.5 cosine of whatever this number happens to be times t minus pi. And at any time, we could figure out where the buoy was. We could figure out its energy from K times X max over 2. We could figure out omega if I gave you the mass was 10 kilograms or something. Knowing omega, you could find K, because this is K over M. Those types of problems, pretty easy, right? They're not hard mathematically. They're just, you've got to know what your variables are and how to find them if you don't know them. But yeah, there's so many examples that you could use of something moving in uniform, or not uniform, maybe simple harmonic motion. Basically anything that has a motion that repeats over and over and over again in nature, you can describe with the equations that we've learned. And if you go back to whatever this slide was, to be honest, this slide right wherever it was, this slide right here contains everything you need. This is everything you need to know from this chapter, other than the pendulum stuff that we learned the other day. But if you got all this down, you're going to find that it's really just a matter of, can you find your variables somehow? Can you find omega? Can you find x max? Can you find k? Or can you find phi by analyzing the situation logically? And then once you have it, just plug those numbers into your equations and you're good. You're done. From there on, it's just some calculations. It's not even hard math. Okay, so that is the last I have to say about that. This is the end. It's been a long, crazy couple months. Had no idea at the start of this that life was going to so dramatically change. But if you've been with me this long, and you've been putting in your effort, we're going to have a final in like a little less than 2 weeks, or about 2 weeks now. Something like 2 weeks. And then we're going to be done. And I hope that you'll go into the final not feeling as stressed out as you did going into maybe exam 2. I think everything we've learned here is much easier because a lot of it is just memorizing equations. You can actually get by in a lot of this by memorizing equations. You don't have to do so much analysis. You do have to know a little bit. In the fluids, you have to know like what the pressures are. And in the gravity equations, you have to be able to figure out, using Kepler's laws, what things are. And in these equations, you need to be able to find your variables. But honestly, I think these are much easier. It's a lot of using equations, not so much trying to derive things or figure things out. I think. Maybe I'm wrong. But anyway, the final will be a couple questions from, it'll be a question from fluids, a question from the gravity, a question on pendulums, a question on oscillations. So chapter 15 is going to have 2 questions on the final. And then we're going to have a question that would be like a question I would give you for exam 1, meaning projectile motion, free fall, some type of Newton's equations. And then we're going to have a question that would be like exam 2, which would usually be energy and some torque. So maybe equilibrium or energy. So if you're looking for what to study, honestly, studying those first 2 exam 2 problems would be a really good place to make sure you solidly know those. And if you felt like you knew them and you did a good job on them, then you're fine. I'm going to give you an extra credit, and the extra credit is that I want you to write up a question like an exam problem. So take a question, really take it apart. Think about it as if you were the instructor. What would you ask? What concepts would you want to know to be sure that someone knows? The point here is that I want you guys to think at a higher level about the exam questions and what you're being asked. Obviously, I'm not asking you so much, what is the acceleration at this time? What I'm really asking is, I want to know that you know how to set up a problem, how to take it apart, how to find the information you need to do a worthwhile analysis of the problem, and how to take it further than just a math number. I usually want to ask some kind of thoughtful question here. Doesn't mean the math isn't important, but honestly, what makes physics hard is not knowing how to do these problems, to actually do the problems. The math is almost pathetically easy sometimes. And I hope you found that as we've gone. What the real trick is understanding what's going on and trying to figure out how to find answers. But anyway, I really do appreciate, number one, that you were all my students. Uh, and number two, that you stuck through this incredibly crazy time. Um, and if you need anything, we're all here. We're all here for you. Far beyond this course. If a year from now or 2 years from now you're struggling or you're excited about something you've achieved and you want to tell me about it, contact me. I'll be there. I wish nothing but the best for all of you, and I hope you all become successful. And I really hope you got a lot out of this class. I hope this class was rewarding to you. The time you spent, the effort you spent, you actually learned something that down the road will help you. But anyway, thank you, and I'll talk to you soon.